Recording started.
Good evening, everyone. Welcome to the Centenary Celebration of the Department of Mechanical Engineering, IIEST Shibpur. Today, we are here for the 26th lecture under the Centenary Lecture Series to be delivered by our Honorable Alumnus, Professor Narayan C on the topic Modern Powertrain Technologies for Electric Vehicles, an overview. Today's session will be chaired by Nihar Vishwas, Distinguished Professor, Department of Civil Engineering, University of Windsor, Canada. Over to you, sir.
Thank you very much, Dewey. Welcome, everyone. And special thanks to for all the organizers for this lecture series, and particularly this one. Dr. Carr is one of our faculty members in the electrical engineering, and I was what should I say, one of the fortunate ones in the hiring committee of Dr. Carr almost 20 years ago. And we were looking for somebody in the electrical machines. That's the area that we wanted a new faculty member, somebody who will be covering both mechanical as well as electrical engineering courses. And that's when we found Dr. Carr, and Dr. Carr actually came from Bangladesh to Japan, from Japan to University of Saskatchewan, and from Saskatchewan to University of Windsor. You can see in the flyer that he is very accomplished researcher, but it does not speak all of the other things that he does. He probably developed the largest research facility in electrical machines and electric vehicles, actually, in Canada at the moment. And he has a very big research enterprise, and he's always looking for good students. That's one of the things that we know. And he's extremely dedicated to the field and also to the profession of engineering itself. So with that, I think I'm going to let Dr. Carr start his presentation. Dr. Carr, please.
Maybe Professor Carr is in mute mode.
Dr. Vishwas, can you see my slide?
I can see your slide, yes, and
Okay.
I can hear you also now.
Oh, excellent.
Yes.
Okay, thank you, Dr. Vishwas, for your kind introduction. I remember that day I came here for interview, and at the end of the day, we went out for ice cream. I remember that. So Dr. Vishwas has been not only on the hiring committee on that day, but since the day one, I have been here. I mean, he has been a great mentor to me, and I dedicate a lot of success that we have achieved as a program to Dr. Vishwas. Even before I joined the University of Windsor, he told me that you should hire this student. I was still at the University of Saskatchewan. He told me that you should hire this student from Shibpur. And I'm glad I did that. That student graduated with flying colors, got his master's degree, and got a job at a power company right away, right? So anyway, so I have been very grateful to Dr. Vishwas for all he has done to me as a person, and also to our program. Thank you for that. To IIEST, I would like to congratulate you on your 100 years of dedication to the development of knowledge, development of engineers who have gone to serve the society, not only just in India, but all over the world. I congratulate you on that. So, and I would also like to thank you for inviting me to this event. I am very honored to be here and present to you samples of what we do here. We are heavily involved with industry like Ford Motor Company, Magna International, Mech. These are very large billion dollar companies, DMV Electronics, and other companies that we work or worked with. So that's a lot of information I would like to share. Those who would be coming to our program in the future as graduate students or visiting professors or postdoctoral fellows, we will share and talk about them. But many information I can't share because of the confidentiality of the work we do. But I have assembled some sample published works that will give you an overview of what we do here at the University of Windsor. As Dr. Biswas mentioned, and I am going to show you later in the presentation, that we have a very good research lab. We are very proud of that. I have been very fortunate to be able to secure a lot of industry and government, federal and provincial government fundings that helped us grow as a program. So I will show you that later in the presentation. So my name is Narayan C. I'm a professor in electrical engineering. I also hold a Tier 1 Canada Research Chair position in electrified vehicles, in electric vehicles actually. And I also established the Center for Hybrid Automotive Research and Green Energy. So that was long time ago. Back then we thought hybrid electric vehicles should be the thing of the future, but it looks like we are skipping that, moving on to electric. So that's why we are doing research on electric vehicle technologies. My background is electrical engineering, so I'm good at electrical engineering, but I also work with professors and researchers from the computational fluid dynamics area to address thermal aspect of electric machines. I work with mechanical engineering professors on the to address mechanical aspect of machines and inverters. I work with computer science to employ softwares and algorithms to solve different problems. So our program is very multidisciplinary. We not only work with people from different areas at the university, but also nationally, we work with a number of universities. Many projects I lead, our program leads many projects that we lead nationally. Okay, so with that, the presentation title is Powertrain Technology for Electric Vehicles, an overview. So, okay, so the outline would be, I will give you, I mean, some of you may not be aware of where Windsor is or University of Windsor, so I will give you a quick overview of that. Then I will talk about that powertrain systems, or we call it drive systems, that we use in electric vehicles, that multi-motor. That means one in the front, one in the back. That's why we call multi-motor. So we do a good amount of research in that area. I will talk about that. Materials is a very important subject. That's not my expertise, but I work with professors. So I'm not going to take credit for that, but they are the ones who did in collaboration with us. And we are very happy about that looking at problems in a multidisciplinary way. Then traction motor design and optimization, that is my core area as an electrical engineer. Then traction motor drives, so that's power electronics. I will touch on that as well, because we use power electronic system to control the power flow from the battery pack to the electric motor to propel the vehicle. So we'll touch on the traction motor drives. And then thermal study is the most important one because you manage temperature, components can live longer, they perform better. So that's why thermal study is another area that I work with various thermal experts to address thermal issues. And they're all mostly from mechanical engineering. And materials, also materials and mechanical engineering, they go hand in hand here at the University of Windsor. And research and test infrastructure, I will show you some, but Dr. Biswas knows that we are expanding our lab. So renovating and expanding, where we'll have many $1 million worth of renovation and new equipment there in our lab, and should be operational within a couple of months. So Windsor, I mean, you can see at the top on the northern side is Canada, at the bottom is US, and this red point there, that is our Windsor, our Windsor. We live here, right over there. Can you see the pointer, Dr. Biswas? There is the mouse pointer.
Yes, I can. Yes.
Okay, because I might use it.
Yeah.
And then if we zoom in there, then you see this is Detroit River. So upper side is Detroit, Michigan, and the lower side is Windsor. And University of Windsor is right there. And you can see, so there's the bridge we call Ambassador Bridge. So our university is right there. So I can see Detroit from here. There's the Detroit downtown. I can see building tops. I'm not sure if you can see. No, you can't. So over there, GM building, General Motors building there, I can see from here. That Ambassador Bridge I can see from my office is right here. So that's our, that's the close proximity, right? Even we go to Detroit for shopping. These days it's a bit tricky. We go, but we used to go even more before COVID. So it's right over there. So, and Detroit is the automotive capital of the US, United States. And as a result, Windsor also grew as the automotive capital of Canada, right? And that's why the focus of automotive engineering at the University of Windsor is significant, right? Because of the proximity, right? So that's why in Windsor, we have over 90 automotive part manufacturers, suppliers there in Windsor. Then we have Ford Motor Company's research and development facility here in Windsor. Stellantis Automotive Research and Development Center right there in Windsor. The building of that research center owned by the University of Windsor, everything inside is owned by Chrysler or Stellantis, right? We have hundreds of students trained through those two research facilities of Ford Motor Company and Stellantis. Then recently there was an announcement of $5 billion battery gigafactory that is 15 kilometers from my office, right over there. And there is electric vehicle related R&D facilities. Then there is Magna is in the planning phase to develop a battery housing manufacturing company in Chatham, about 80-90 kilometers from Windsor. So that shows that not just traditional automobile, but also the now and near future automobiles like electric vehicles, that Windsor will still have a significant presence in this automotive footprint in Canada, right? So that's why our research is aligned with that, right? That if the industry grows, we grow as an automotive engineering program, both academically and research-wise. So this is one of the buildings of the University of Windsor at the left side. Then this picture is a bit old. That's why you see our research and innovation office building is still under construction, but it's now operational for a few years. So this is our Center for Ed Lumley Center for Engineering innovation, our engineering building, and we have three major programs. The largest one is mechanical, automotive, and materials engineering, and that also includes industrial. We have civil and environmental engineering, where Dr. Biswas, that's his home department, and I am in electrical and computer engineering. So these are three major departments we have, and all three departments are located within this building. And my lab is kind of, you see this bar going down, so kind of this is the eastern side, south side, so kind of southeast side of this building. That's where SARS lab is located. This is a picture within the building, so it's a state-of-the-art building. Some of you might know the university and the government spent about and also fundraising and everything, $112 or so $1 million. So this is a very fantastic building, and it hosts I think 80 or so labs within this building. So we have a very good engineering facility at the University of Windsor. So Powertrain Technology, some of you may not be aware of that. So this is from Google. You do Google search, you can find this kind of fancy pictures. So this is Audi, from automotive company Audi. So I thought I will download that and show you to introduce that when I say powertrain, what do we mean by that, right? Powertrain means that you have an electric motor, that is kind of the electric engine that propels the vehicle, electric motor, right? And then there should be a motor controller, power electronics and control that we call the controller. So that controller controls the power flow from the battery pack, right? So the battery pack is on the floor. So this is the battery pack, right? Mostly lithium-ion batteries are used. So this is the battery pack. Then there is a motor controller there, and the motor there connected to the wheel, right? Connected to the wheel. So you can control the power flow through that controller from the battery pack to the motor, right? So the powertrain I am talking about includes the electric motor, power electronics, and control. So that's what I do. So I am calling that as the powertrain technology, right? So here in the case of this particular vehicles, they have one motor and controller in the front, one motor and controller in the back, right? We call that all-wheel drive multi-motor system because we have more than one, right? So we have one motor and drive or controller here, one there, right? So then this is the battery, and we need to charge electric cars. So this is the charging port, right? We used to do some charging work. Right now we are not doing. Usually I go where industry money takes me in the area of what we can do, right? You can use power electronics and control to build battery chargers. So we used to do that, but presently we're not doing much. So our focus and today's presentation is about here, the motor and the motor controller, motor, power electronics, and control to be specific. And similarly, the similar unit is there, but they're different in size. So that's why they look different, right? They're different in size, and depending on how much space you have within the vehicle. So we control the size and shape of the motor and power electronic system. So our focus will be here and here. So let's talk about multimotors. So I have a PhD student, Marco. So Marco is working on this, optimizing this motor systems. If I go back to the previous slide, then you see there is one electric motor, which is the electric engine, just to let you know, and another electric motor in the back. But which one should be how big? How do we know, right? So that's why, given a vehicle in mind, given the application in mind, we can optimize the size for better vehicle performance, for better energy conversion efficiency. So Marco's project is on determining what would be the actual size of the front axle motor and rear axle motor. So let's call it the front motor and the rear motor, right? So this is another picture of a multi-motor system. This is from Ford Mustang Mach-E. We have one in the lab. I will show you a picture we have. So it has one motor in the front, one motor in the back, and the back rear one is usually larger and front one is smaller, because when you talk about acceleration, right, the weight and the vehicle, everything shifts to the back, right? So that's why for better acceleration, better performance, the rear motor has to be larger. Front one for performance, additional performance improvement, like when you are slowing down, we capture the energy. Then the front motor, because we are slowing down, we are moving forward. So everything shifts to the front. So then the front motor becomes a generator and extracts the energy from the wheel or from the vehicle, that from the kinetic energy, and sends back to the battery pack for to extend the driving range, right? So this is so we have a project with Ford Motor Company, and one part of it is to determine what would be the size of the front motor, what would be the size of the rear motor, right? So the objective of Marco's project is to optimize vehicle dynamics and efficiency performance by varying that motor torque, right? Torque split, that you need a total amount of, say, 500 Newton meter. Then maybe the front motor, maybe 150, rear motor 350. So the torque split ratio, determine the torque split ratio in a way that we can optimize the vehicle dynamics and the efficiency. For electric vehicles, I mean, still driving range is an issue. So that's why energy efficiency is extremely important, that whatever we can do to improve energy conversion efficiency, we'll be doing that, right? So objective is to improve energy efficiency, improve performance at the same time. And for that, what would be the torque split ratio, right? So then we're calling it MMEP, multi-motor electric powertrain. So to improve vehicle efficiency and stability control, right? So they can come in two shapes. One we call centralized, other is decentralized, right? In the centralized version, you will see the battery pack there. Then the inverter. Inverter is part of that motor controller. It controls the power flow from battery pack to the motor, right? And both motors could be connected side by side, right? Side by side. Then the gearbox, then the wheel, right? Axle of the wheel. So these two motors are at the center of the vehicle. That's why we call this centralized architecture, right? Then there could be another one where the one motor in the front, one in the back, and then we are calling that decentralized, right? So the top one you see, the picture, Mustang Mach-E, so one in the front, one in the back. So it is decentralized multi-motor system, right? Just the previous picture of Audi, that's also a decentralized architecture, right? So just like any other research project, he did literature survey to understand the knowledge gap, then understand what his contribution would be. So idea is to that in a decentralized architecture, that develop an algorithm which is he developed non-dominated sorting GA to optimize vehicle performance, to determine ultimately the front motor size and rear motor size. He published a couple of conference papers. He is relatively new in the program, but he already published 2 conference papers, right? So then, just like any research project, that he has a number of steps. He developed a method and applied that algorithm, that multi-objective optimization algorithm he developed. He applied that to determine the vehicle performance and efficiency. Just a couple of sample pictures. I mean, the papers are there. If you are more interested, you can read those papers to know more about this this subject. So as you can see, the vehicle velocity in meter per second, which is this is kind of 28 meters per second, should translate into about 100 kilometers per hour, right? That's usually our highway speed limit, but there's 110 as well, but usually it is 100. So we set 100. And also when you go buy an electric car or any car, then it would tell you that it would get to that 0 to 100 kilometers per hour speed within a given number of seconds, because people love speed, right? So that how fast can you get to that 100 kilometers per hour? So in the case of us, it is a little less than 4.5 millisecond to get there. Electric cars are really fast, right? When you drive a Tesla or Mustang Mach-E, it goes really, because electric motors, they produce torque really fast. So that within a short period of time, it gets there, right? And also, if you can see that this is the target velocity. This is in meter per second, so could be confusing, but this red dashed line represents target velocity of 253 kilometers. And how fast can you get there, right? How fast can you get there? So just to show that the model is performing and achieving that results. And out of that, we determined that 75 to 25 rear front motor size, that rear motor size should be 3 times bigger than the front motor side, torque-wise speaking, right? So that's what we found. And then we will design electric motors with that kind of specifications. The front one should have rear one should have 3 times the torque in comparison to the front motor. So materials. Materials is not my subject, but I collaborate with our materials researchers. As a result, I have some knowledge, but I am no expert of materials. But opportunities are there, because it starts electric machines, it starts with materials, right? So our objective is to improve material properties, right? To develop, improve traditional materials like electrical steel, copper, aluminum, and also to look into new type of materials that could be used in electric machines, right? So we are looking at traditional and non-traditional materials to build electric machines. But anyway, what they do, if we use materials with better electromagnetic properties, it can improve efficiency. Efficiency goes up means power loss goes down means heat production goes down, right? So we need to develop materials towards improving efficiency, towards improving thermal performance. Then better materials, you can use less material to produce certain torque, a certain amount of torque, right? So materials would influence the torque density as well, right? Cost is another factor, right? Some materials are costlier than others, right? So we need to take cost into account. So that's why material is so important, right? So because of those reasons. So this is one that we work with a number of professors, then also companies, one company, then Canadian government national lab to look into materials, and one material that we looked at in collaboration with one national lab and Dr. Idrisi. He's a co-author of the paper. Afsane Idrisi, Lucas Chauvin was her student. Mehdi was her PhD student. Shruti was my PhD student. Hima was my PhD student. Yuliang He is a researcher at Canadian Government Materials Lab. Dr. Chong is the R&D manager at Ford Motor Company. So you see the collaboration that my lab, Dr. Idris's lab, government lab, Ford Motor Company. So you see the amount of collaboration and back and forth information exchange that is really significant. This is one of the benefits of the students working in our lab, that they truly experience, right? Not only working on industry problems with industry, but also this whole collaborative approach that we employ in solving problems, right? So anyway, so Suruthi, now she is a research and development engineer at Magna, and Hima, she is a professor at Carleton University. They are all recent in the last 2 years. 2 years or so they graduated. So, and they are all accomplished people, right? Both of them are from India. So Shruti developed this model, right? And this model will employ the materials our government lab and our professors are developing, right? One of those was non-oriented electrical steel with optimum texture, right? So to improve the electromagnetic performance, right? Like permeability, higher the better, right? Then higher permeability means higher efficiency, means lower loss, right? So that's why they developed this nose material, non-oriented electrical steel, for using in the electric machine rotor, the rotating part of the motor, and the stator, the stationary part of the motor, right? Then so they developed that model material to improve, excuse me, magnetic properties, which include higher permeability and also core loss. Core loss is a loss that happens within the motor. It's an electromagnetic loss, right? So, and if we can improve the permeability, lower core loss, then the overall performance of the motor can go up, right? So then we compared the performance of nose, non-oriented electric machine, with GOES, right, grain-oriented electrical steel. And also the one developed by our team versus the one commercially available, right? We are not always successful, that we are not always able to develop materials that are better than what is available out there. Not always, it takes time, right? So we have to be very patient, a lot of uncertainties. We don't have access to the right infrastructure sometimes. So sometimes the process is long, but once we get started, at some point, we are able to develop materials that is better than the one that is available on the market, right? So we developed machine models with all sorts of materials, nose, GOES, ours versus commercial. We used those properties, fed into the machine model, and then we found that optimized nose results in lower core loss, right, than the commercial GOES, grain-oriented electric machine. Then we have lower effective resistivity. Less resistivity means less loss, right? Less loss means less heat, right? So that's why resistivity is very important, right? And then reduction in core losses than commercial nose. But you can see it is not all rosy yet. Maybe with more research, we will get there. If you look at the torque and power performance, and you can see the studied materials in terms of torque and power that is still lower than what is available out there. So there is still room for improvement that we can see here. So the research is ongoing. Then we also looked into aluminum. Copper is the one we have been using over a century as winding material for electric machines, right? But Aluminium has made significant progress. So our national lab, in collaboration with our materials professors, thought, and I was part of the discussion, of course, that why don't we try out aluminium, since aluminium made good progress, right? Aluminium is lighter, aluminium is cheaper, aluminium has better thermal conductivity, right? Thermal capacity, right? So, but aluminium has higher resistivity, right? Aluminium has other not so good mechanical properties, right? So there could be durability issue as a result of that, especially winding, it goes back, right? So in that end turn, aluminium does not perform as copper does, right? So, so since aluminium has higher resistivity, so that's why you can see that torque production and the is a little less when it comes to aluminium in comparison to copper. And then we developed models, identical models, one with aluminium winding, one with equivalent copper winding. Then run the motor in a drive cycle environment. I mean, those who are in automotive area, we know drive cycle. It's a kind of, we put the car in that drive cycle and repeat, right? That if you see figure A, we call urban drive cycle, right? That speed goes up, then it goes down a little, goes up, then the vehicle comes to a stop at a signal, then it stays there for a minute, then again you accelerate and go here, then another signal comes down. So we can program the drive cycle and run the motor as per that torque, speed, and as a function of time, right? So with that, we can calculate the loss from there, the efficiency of the motor, right? So, and we can see that in the case of aluminum, it is expected that the efficiency would be lower because of aluminum has higher resistivity, right? So, and that's what we found, right? That aluminum winding-based electric motor has lower efficiency, but winding cost would be much less, right? And the motor would be lighter, right? Because winding aluminum is lighter. So these are not something that is groundbreaking. Oh, we did not know that. We just found out. It is not that. It was expected. So we found it. But the key challenge here in this project is to improve the mechanical properties of aluminum, right? And how to reduce resistivity, right? So those are the major challenges that we are addressing. Even we are talking about it, that how to do more research on aluminum to make it comparable to copper winding. But that could be that would produce some breakthrough impacts, right? So then we look at other type of materials that usually you would not see, but you will see motors are surfacing with that kind of new material we call soft magnetic composite, or SMC. We use in the stator and rotor electrical steel, but we can replace electrical steel with soft magnetic composite, right? So we have done some theoretical work. We have not built any machine with soft magnetic composites. So we had developed a motor in software. It's called axial flux. Axial flux motor means that axially it is a bit shorter, and diametrically it's a bit wider, right? It's like a pancake, right? So we call that axial flux because flux flows in axial direction. So that axial flux machine we developed in software using soft magnetic composites. So we developed a number of models. One with in the stator soft magnetic composite, rotor electric steel, or soft magnetic composite in both the stator rotor, then electrical steel in the stator. a soft magnetic composite in the rotor. So 4 models we built, and from there we see electrical steel still produces better performance in comparison to soft magnetic composite. But soft magnetic composite can bring you can make the motor smaller. The wastage of materials could be less if we use soft magnetic composite, because you build things to its shape, right, using soft magnetic composite. So wastage is less. That means lower cost to manufacture. So we built 4 models. We did a comparative performance analysis, and we are using the results to see that we should build one. But it is not easy because we don't have the infrastructure here, or many manufacturing facilities, they don't have that infrastructure to build machines with soft magnetic composite. So, but we are still working on this. And if you want to understand more, this paper we published in IEEE Transactions on Magnetics last year. So please feel free to download and read. Then electric motor design and optimization. So that's the materials that for stator winding, we can use copper, we can use aluminum, we can use carbon nanotube, but it's extremely difficult to do that. Still, people are kind of looking into that. Then for the stator rotor core, we can use electrical steel, we can use soft magnetic composite. Then in induction machine, we can use high performance aluminum to as the rotor case within induction machines. So different types of materials out there. We are playing with them to see what would be suitable to develop next generations of electric machines. Then we do optimization, then we do prototyping and testing, right? So when it comes to designing and optimizing, our biggest concern is always how can the small motor produce a lot of power, right? Or a small motor can produce a lot of torque. We call that power and torque densities, right? That given within a given liter of size, volume, how much power, how much torque the motor can produce. So increasing more power for a smaller volume is always a target. Reducing cost is the biggest one to bring the electric vehicle cost down. And of course, efficiency improvement, thermal performance improvement, overall performance improvement. Those are the primary objectives, big picture objectives. So there could be different scenarios. So here in this case, we call it direct drive EV. That means the motor is directly connected to the wheel, right? In that way, you can get rid of the transmission. And if we can get rid of the transmission, then the vehicle efficiency would go up, right? Then less component count, then lighter, right? That means we don't have transmission, so we have more space for the occupants in the car, right? So that's why direct drive. So direct drive means the speed is low, torque is more, and motor size is a function of the torque. You need more torque, the size gets bigger. In a small cars, we don't have a lot of space, so we cannot accommodate big motors, right? So for larger vehicles like electric truck or electric bus, right? That's where you have a lot of space in the floor. So that's where this direct drive motor can go, right? So we worked on this direct drive motor, low speed, high torque, and we looked into permanent magnet machine. And since it's a large machine, so you need a lot of magnets, and magnets could be expensive, number one. Number two, in North America, we don't produce a lot of permanent magnet. They mostly come from outside of North America, and that's a huge security concern for us. So that's how we can use a permanent magnet motors for obvious benefit of better performance with permanent magnet machines and smaller in size relatively in comparison to induction. That it's a permanent magnet machine, but still how we can reduce the amount of permanent magnets we use in the machine, right? So then Hima Dhulipati, so uh, developed this machine with higher speed, lower torque, with reduced use of permanent magnets, right? We call that consequent pole, that every other pole is a permanent magnet, and we are using the iron in the rotor as a pole in between permanent magnets. We call that consequent pole architecture, right? So Hima developed that model. Then she also developed a prototype. You can see on the right, left. So this is the prototype Hima built, and this is a dyno we have in the lab. So then we connected the machine to the dyno. Then you need to control the machine, right? Say in those drive cycle. So we can program the drive cycle there, and then under speed as a function of time condition, that power will be flowing from a DC supply, which represents a battery pack, to the motor, and we extract the motor performance, right? So we have been very successful. Then Hima designed, so this is a small version, and we were happy with the performance. Then we built a bigger machine, full scale machine, right? We prototyped it, but we prototyped the stator, we prototyped the rotor. So now we have to build the housing, right? Housing. I collaborate with mechanical engineers to build housing with cooling channels and everything. So we are in the process of doing that to complete that full scale large machine. And then we will be testing that machine for performance. So that's the low speed machine. Then in regular cars like Tesla or Mustang or Audi Tron or other electric cars, you'll see high speed electric machine, right? 10,000, 14,000 revolutions per minute, right? So higher the speed, lower the torque. Lower the torque means smaller the motor. Smaller the motor means lighter it is, and it occupies less space. So that's why high speed. So Shruti, she is now an R&D engineer at Magna designing machine. But designed a high-speed permanent magnet machine, right? And the objectives are similar: higher torque density, power density, higher efficiency, higher performance, lower cost, right? And also, since she's using a lot of permanent magnets, as the motor operates, temperature will build and the magnet might demagnetize. So she had to look into that as well, right? So that's why she designed the architecture in a way that there could be other mechanism to reduce the current loss, hence the heat, right? So that's what she did. So she built mathematical models, then she designed a machine, and that machine, again, there is a smaller version of that. This is the larger version, right? So there's a smaller version of that we prototyped, tested. We are happy with the performance. Then we built the full scale 100 kilowatt machine, right? 100 kilowatt machine. So we did some preliminary testing on the stator. You can see the outer part of the motor, and the rotor goes straight in, right? And then with a company, we built the housing with cooling channels. But when we put everything together and pumped cooling with a certain pressure, we see cooling is leaking out, right? So then we went back to the design table. And it is being done at our partner facility, industry partner facility, right? Two companies are involved. So then we are kind of that we'll develop two now, one with improved cooling channel and other with kind of remachining the existing one we already developed to see if we can still use. So once the whole motor is done, then we'll be doing performance testing, right? And these motors, full scale ones we developed, I mean, we started our project, and at that time we had Ford Focus electric vehicle motors in the lab. We still have a number of them. So we did some benchmarking to understand where the technology is. We used that information as our baseline, and then we set our own target depending on there is Department of Energy, they have some targets when it comes to motors controllers, and we try to achieve that. And so far successfully, we have been there almost. So that means this machine is better than the machine we started with, right? But we need to understand the benchmarking we did with the previous motor is 5-6 years older, 7 years older, right? Technology back then was not as advanced. So it is not quite an apple to apple comparison, but at least at a research lab level, work done by students and postdocs demonstrate that yes, we can get there. And they work with industry partners, as you see. So that's why they are sometimes before graduation, they are hired by these automotive companies. So then power electronics, it's too electrical. So I just put a couple of slides just to introduce you, because here from mechanical side, a lot of heating is produced, right? So this is the breakdown of Audi inverter. Inverter is the power electronic part, then the control on the top. You can see this control board. Here you can see controller board. And this is the power module you see. That's where AC is converted into DC, DC power is converted into AC power, right? So that's what it does in a controlled way to control the power flow between the battery pack and the electric motor, right? And this power module, as it converts AC power into DC power or DC power into AC power, it produces a lot of heat, right? So that's why that heat has to be dissipated. So I work with two professors, one on motor thermal, one on power electronics thermal. They are developing thermal models and then prototypes and demonstrating the performance of their prototypes in front of the industry partners, right? So power electronics, there are different types of power electronic switches that controls the power flow, right? And depending on what type of switches we use, they produce varying amount of heat, right? And that is the heat that has to be dissipated, right? So we use water glycol to pass through the bed of this power electronics switches to extract the heat out, right? And use a sealer and circle back the coolant is circled back into the power inverter module to cool them down, right? So the whole inverter looks like this, right? This blue is a capacitor bank, and these are control and power electronic module here. This is three-phase power in and DC out in the back, we can see, and there is cooling channel that coolant will flow from here to there. So we develop thermal models to understand how much heat would be produced for a given operating condition. And then we develop cooling mechanism, right, to cool the inverter down, right? So junction temperature is the temperature right after that power module, the heat there, right? So there, unless you cool it effectively, the materials will degrade with time, and the inverter will not last long, and it will not produce enough power to begin with, right? The control also measures the temperature. So if temperature goes up, the power production or power conversion would be less and less as temperature goes up, right? So temperature, heat, thermal analysis of power electronic inverters is a big research area for us. So thermal modeling, so that's the power electronic inverter. Then for electric machine, so as you see, as the motor operates on the right side, the temperature goes up. So we start from here, from the shaft, all the way to outer side of the housing, right? And you can see from shaft all the way to the motor frame, right? So we build that kind of model, so we call thermal network model, right? So that we calculate thermal resistance depending on materials, depending on the dimension of given parts of the motor, right? And we calculate thermal resistance, and then and they're lumped, right? So that's why we call lumped parameter thermal network model, right? So develop model. Loss is we run simulation on the motor to understand the loss at different points within the motor. Then we use the loss to calculate, feed that loss into this machine lumped parameter thermal network model to calculate temperature. Then we determine how much cooling we need, right? So that's a big area for us. So we also build housing with all sorts of cooling channels. We do thermal analysis in addition to electromagnetic analysis, we do thermal analysis. Then there is the structural analysis, and they all influence each other, right? Electromagnetic is my core area, but thermal analysis, we have thermal expert. Structural analysis, we have a structural expert, right? So as you see, it's kind of an iterative process, collaborative process, right? To develop electric machines. And Pratik, he is now employed by another automotive company. He did his master's, so he did good amount of work on thermal modeling of electric machines. He had mechanical engineering background. Marco, the first two papers, he comes from mechanical. Pratik comes from mechanical. Tauhidi is another student, graduated, got his master's degree in this area, came from mechanical. Then the structural, I have a student, PhD student, came from, again, not electrical. So as you see that we have people that students from, I mean, more than 50% from electrical, 30% from mechanical, uh, and the rest from computer software. Then from even background in computational fluid dynamics, right? So we have students from all disciplines, right? It is not that I'm an electrical, that's why we only do electrical stuff. Half the work is mechanical, right? Then we have been fortunate to receive good amount of infrastructure funding from the university. We are investing many millions right now towards infrastructure development, lab expansion. We have 4 office areas within the lab for industry partners to sit down there to work with the students, right? So that's why our lab is a place that fosters multidisciplinary collaboration, right? With industry, with government lab, with professors from various disciplines, with the students in the lab, right? So we have received funding so we can test prototypes, motors, inverter prototypes built by various companies. They bring their prototypes to our lab, then we test them for them, right? We do that almost on a daily basis, right? And this is kind of, sorry. So this is kind of a test facility that we also work with a motor inverter tester manufacturer, right? We developed algorithms, test methods, try them out in the case of this system. If we are happy with the performance of the test methods, then the industry partners use them to build their next generation of testers. So this is one of those testers. A few more pictures. This one is the same one you just saw from another angle. Then this is a small dyno tester. So we put torque speed as a function of time here, and we get all the results there. We can also control the motor from here to test the motor under different operating conditions. And you see an inverter right behind there, a big inverter that is designed by Dr. Mukherjee of IIEST. So we have been fortunate to have him in the past. These days he's very busy, but we are hoping that our other colleagues from IIEST would visit us and make it a win-win situation for both of us, for you, for us, and ultimately our students will benefit from there, right? So the inverter right behind this rack, you can see well, so that is designed by Dr. Mukherjee. This one also was designed by Dr. Mukherjee, built in India by Semicron, right? This one, the one behind. So we have a good Indian footprint in our lab there. So this is Ford Focus electric vehicle motor that we used for benchmarking in the past. This is another motor. So these are students working there, visiting professor from Turkey. He is completing his master's. He graduated working for another company. Aida used to work on machine design. She had a bachelor and master's in physics. Then she came to me. I said, what can you do with us? She said, you use materials. I said, I have physics background. I can work on materials, right? So she did her PhD, designed induction machines for electric cars. Now she designed machines for another company after her graduation. So she finished her PhD a couple of years ago. And this is a vehicle level test dyno that we are commissioning as we speak. We are building it right now. So we'll be commissioning, should be here in a month or so. Then we'll be putting our the vehicles we have in the lab on the tester, that you develop motors, you develop inverters, the powertrain we develop. So we'll be benchmarking existing electric cars and then take their powertrain out, put our powertrain in, and again test at the vehicle level to see the performance. So that's that's what this dyno, chassis dyno we call, would do there. And we have one big dyno. We are commissioning, designing and commissioning two more 250 kilowatt dynos. I did not show you here because I did not want to show you premature picture when the system is ready, but we'll be sharing with you with those who are interested. So that's how our lab is expanding and growing, given the significant electric vehicle research opportunity we see. So we have a Mustang Mach-E electric car in the lab. We have a Tesla electric car with full self-driving capability in the lab. This is a Prius hybrid we bought 8, 9 years ago. I was younger back then. You can see that from there. So this is a hybrid electric car we got many years ago. Before that, we had an electric car. We had an electric car that ran on lead acid battery, right? So we have been with electric vehicle technology for quite some time. And as a result, we have made significant progress. So I think with that, I think I took longer than I should. I think that was all. Thank you.
Oh, that was perfect. Thank you very much. Thank you. It was excellent presentation. It was very informative, but at the same time, you kept it at a level that some of us who are not in the field, we could still follow. I am sure the students really enjoyed it. And right now, the floor is open. The floor is open. So any questions? Any questions from anyone? Any questions? Whether related to presentation, this presentation, or something that you want to know? Anything? Please.
Thank you, Professor Kaur. I really liked your presentation. As Professor Bish has rightly said, that you started ground up and moved up very fast and kept us abreast what the heck going on in the electric vehicle. Now, there is a general interest all across the board about electric vehicle. Let me put the question up front. One of the objective in our material cycle, by the way, I'm a mechanical engineer and I'm still hardcore mechanical engineer. But my question is about your materials regarding your magnetic material, where you are really trying to get improved electromagnetic properties, basically, and improve core loss, etc., etc.
Yes.
Now, you tried different types of materials, okay, different types of alloy, steel, grain, oriented, non-oriented, copper, aluminum, alloy, etc., etc. I'm just wondering whether your team has ever looked into so-called made glass. Made glass was in vogue when I was a junior engineer in 1980s by Allied Chemical. Actually, it was introduced by MIT. The concept was very nice. Concept was that if you take any steel alloy or any alloy for that matter, then rapidly quench it, we are talking about million degrees C per second, then the alloys will not have the opportunity to crystallize. They become amorphous. So what is happening, their characteristic totally changes. Allied, and we spend literally hundreds of millions of dollars. And one of the key tagline was that minimum core loss and maximum electromagnetic efficiency, and they are geared towards the application for utility companies or electricity. We spend a lot of time, a lot of money. For many reasons, it didn't work out. Obviously, nowadays many people do not know even what is made glass. But I was just wondering, given the requirement of electric vehicle, that may be an option. I don't know whether you looked into it or not. I'm just asking you. We'll go from there.
No, thank you. Thank you, Dr. Sarkar. That's an interesting question. So we have not looked that kind of material. You mentioned made glass.
Made glass, metallic glass.
Oh, I see.
Let me tell you a little bit more about it so that you understand.
If
The
it is
process is relatively simple conceptually. You take a ceramic pot, melt it, metal, whatever you want, any alloy, then pressurize it. And the end of the pot, and there is a slit. Or it could be a hole, it could be a slit. Pressurize it.
Yes.
Now it will come out at a significant speed depending upon the combination of the parameters. Okay, then it will be thrown into another rolling cylinder, and the rolling cylinder will be cooled again. So basically, high melting alloys, molten metal alloys, come and directly hit a chilling cylinder. So it immediately freeze. And your job will be to wind it up as fast as possible. And that we made a lot of, literally we made millions of miles of metals. That is one step. And those things they clearly say, I may have some literature somewhere in my boxes, old boxes. I can send you some information.
Please.
Another interesting part was done by another Indian there. What they did is that they took this metallic glasses, they powdered it. Then using the heaping process, hot isostatic pressure, they could make almost any shape. They maintained many of the properties. So these are the two areas, we can talk offline, but I thought that this is a wonderful opportunity for electric vehicle where core loss is a huge deal. Because core loss will lead to a lot of high temperature, degradation. Okay, and those history curves of the magnetic material was wonderful, wonderful. We have it, so we can talk offline. But I was just wondering, just ask your students to do some research on made glass by Allied Signal in 1980s. Then you'll definitely have some. Or you can call me later on offline. We can talk. Thank you.
Okay. No, that's interesting. I mean, this material certainly has some good properties, electromagnetic properties. When it comes to for utilities, we have either 50 hertz or 60 hertz machines. When it comes to electric cars, we want to make them higher speed. Higher speed means higher frequency. And also the temperature extremities in case of electric vehicle motors are a little higher. So at high temperature, high frequency conditions, especially core loss is a function of frequency. So I wonder if the loss would go up, but since it has good other magnetic properties, certainly, I mean, we should look into that, and I will look into ask one of my students to see or know a little more about this material and prospect of using it.
For your student, for Google search anything, suddenly I realized the other name. This is another Bengali guy. His name is Dr. Ranjan Rai. He got his PhD from MIT. Okay, so he came up to. Now there are a lot of people I can give your names later on. Just suddenly I remember Ranjan Das name, Ranjan Roy. Of course, he's now retired. He worked on those things. Okay, I was in the peripheral application side, making this mid-class, those machines. I was involved in designing and that was.
Okay. Okay.
Thank you very much.
Dr. Kaur, yes, can I put up two questions really in a small way? One is we all know that all mechanical, electromechanical machines totally depends on the ambient. It has to throw away the heat. So ambient is God in the design of electromechanical machines. So you are doing the work in Canada. I've got two questions. You are doing the work in Canada with some kind of ambience. Now, how do I stand? How do you interpret these ambience corrections in other countries like India, like Iraq? This is my
Yes.
first question. Second question is, with the price of lithium going sky high 6 times in a year, what your laboratory are working on new method of batteries or something? These are my two questions.
Okay, thank you, thank you. Those
Thank
are
you for
excellent
the
questions.
lucid lecture. Thank you. But one criticism, sir, your carbs and your datas are not for old people like me. I am 82 years old. I have graduated in 1961. It requires great strength on your eyes. It strains your eyes, the letters and the carbs. That is one small criticism. Thank you.
Ochuda, LG and Sony is waiting on a 27-inch monitor for your home office.
It doesn't solve the problem. Doesn't. I have got a very large monitor, honestly. Honestly, I have
No,
got a
I'm kidding. Since I know you, I saw your home office. I have the right to comment on that, right?
No, please. You have got every right to say anything. You are my boss almost.
No, no,
You
but
have got so much of knowledge.
no, I just have sincere appreciation for Professor Biswas for bringing Professor Kaur to this forum. And it's basically whenever I approach Professor Ghosh, Sudeep namely, so he kindly agreed and host Professor Kaur. I guess this is a wonderful opportunity for our mechanical engineering community, although it's a sleeping opportunity because for any mechanical engineer, automobile engineering is a big subset of that, and slowly seeing that the internal combustion engines are going and it's basically software driven on wheels. And Professor Kaur and his team is doing extensive work on that. What I would just like to say that Professor Kaur, just a request as a B College alumni, that please be in touch with our faculty groups. And of course, Nihad is our biggest interface, and inspire them with your work, especially since this work is going to continue for another decade plus time. So I sincerely appreciate your help in coming to this forum, and just an honest appreciation from an alumni. Thank you.
Okay, no, thank you for inviting me.
Very good.
I-
Very good,
Yes,
Biman. Very nicely put, Biman. I also appreciate Dr. Kaur's work. It's a beautiful work. You have put up The work
Yes.
you are doing very cleanly, nicely. Thank you very
Yes,
much.
but thank you for that. I mean, I'm addressing your, answering your questions, but before that, I mean, uh, it's a collective success, right? I have been fortunate to be in the front of that, but it is, I always tell I'm surrounded by good people, right? So it's a collective approach. It's a success that I dedicate to the people working with me, right? So it is not just me. There's a group of people, large group of people, both at the student level, postdoctoral level, faculty level, administration level, government level, that they all uh, saw that this is an important subject and rally behind all this for a long period of time to get where we are today. So going back to the previous two questions, one is the thermal issue. I mean, I always tell them that if you are in Manitoba in Canada, in winter, it could be minus 40 degrees, or even in Saskatchewan, Dr. Biswas mentioned that I was a postdoctoral fellow there. I lived 3+ years. So in winter, it could be minus 40 back then, right? Or if you're in Arizona, in summer, it could be close to plus 50 degrees Celsius, right? So then one of the biggest limiting factors of any conversion device, and electric machine is one of them, inverter is another them. Electric machines, they convert mechanical energy into electrical or electrical into mechanical. Then the inverter or the controller converts AC power into DC, DC power into AC at varying power level, right? And the limiting how much power they would develop, temperature is the one that determines that. So the question is that when we design, thermal should not be an afterthought, right? It should be thought at the time we design a machine. Look at the materials with higher thermal, that the materials that would perform well at higher temperature, right? Then design cooling system in a way. Right now, I mean, you see a lot of machines rotor cooled, stator cooled. I mean, new cooling methods coming up. So what we do in our lab, that considering all those thermal conditions within and outside of the machine, outside of the machine, we don't do much, but we can put the machine inside a furnace, elevate the temperature to plus 50 degrees increase from ambient, and see the machine performance. But internally, we are doing it. For example, we have cooling systems that can control the coolant temperature from minus 20 to plus 60, 70 degrees, and see the motor, see the inverter performance at varying cooling conditions. So that's the thermal aspect we are looking at. Noise vibration is something we are working on. We have a professor in noise vibration. I am trying to collaborate with him more. We have done that in the past, published a paper or two, but we will need to focus on that more. Industry, sometimes they will come to you, do noise vibration research. Harshness wise, it's situated within the car, not too much exposed. So just in industry facility, we have all sorts of chemicals and hazardous environment around the machines. But in case of the car, it's kind of compartmentalized. So environmental harshness is not a big issue, but temperature, humidity, those are issues, right? So, so those are the things in the case of electric vehicles, motors and drives, we are looking at when it comes to harsh conditions, as you correctly, rightfully pointed out. To answer your second questions, that I work with professors from across the country, and who are expert. I'm no battery expert, but those people are expert in battery areas. And lithium ion battery, I mean, I tell that it is kind of the new oil, right? Right now, you see a few countries dominate global economy because they have oil. In the future, if you have battery manufacturing facilities from all the way to critical mineral to battery pack development, then you have that oil at your hand, and how powerful that is, right? So it is very powerful. In Canada, Canada is the only country I know, as far as I know, that it has got all the critical minerals to build batteries, right? We have lithium, we have graphite, we have nickel, we have uh, any other and other materials, right? Copper, aluminum, steel. I mean, but Canada has very tough environmental regulation that did not allow this industry of mining, processing to flourish, right? Uh, and that's why if you can do that, but extremely difficult given the regulations we have, and as a result, the process is very costly, right? So now we are kind of working on a plan right now that is kind of developing policies that how from exploring minerals, then mining, processing, building battery cells, building battery pack become easier for the country. We develop that supply chain and we become independent, right? So, but cost, given the situation, cost is extremely high because of availability, because of processing, because of building, and only a few companies and few countries are doing that. That's why they are very costly. So their performance has gone up over time as we do more research and development. Batteries are getting smaller, producing, delivering more energy, right? Getting lighter, getting safer, right? So those things are good, going in the right direction.
Another 10 minutes.
Still, production point of view, still we need to work on, which is costly, and it is 1/3 of the cost of an electric car. So we'll need to look into that. And also we need to look at, say, you see those two electric cars right there. 7 years later, their performance will degrade, battery performance, right? And I'm selling my car to get a new one. The person buying my second-hand car will not buy it because the battery is no good. So then we have to replace the battery with a new one. And that could be a costly proposition. So how do we do that? Do I throw my car away 7 years, 8 years later? But we drive a car for 13, 14, in some cases, 15, 20 years, right? So, so that's why the battery pack will play a big role in the coming decade, for sure, starting from the cost, then performance.
Thank you very much, Dr. Kaur. Any other question from
Yes, Nirda, I have two questions.
Okay, please.
At the outset, again, I would like to express my profound thanks and appreciation for Professor Kaur. It's a wonderful talk, Professor Kaur. I have some questions. These are not really questions pertaining to your presentation. Questions are generic in nature, mostly curiosity driven. Usual understanding is BLDC motors or permanent magnet synchronous motors, PMSM, or three-phase induction motors. These are the usual choices for electric vehicles. Now, how do you really go about the specific selection? Does it depend on basically the overall watt or overall horsepower of the car, or how these are selected?
It's a very good question. I mean, you saw these two, one Tesla, one Mustang. Tesla traditionally uses induction machine, while Ford in Mustang and many other electric cars, or most electric cars, use permanent magnet machines.
PMSM.
PMSM. So
BLDC, are they used, or
BLDC, yes, permanent magnet synchronous AC machine. So that's the mostly used one. So we worked a lot on permanent magnet machines because the company we worked with that they wanted us to develop a better version of their permanent magnet machine. So that's why we used permanent magnet machine. But with permanent magnets, we have security issue that if we are not able to import permanent magnets, then what we are going to do, right? So what are the alternatives? Although we have a good amount of rare earth element used to build permanent magnets, we have that reserve in Canada, northern part of the country. But because of the processing could be very not environmental friendly, right? So that's why, because of tough environmental regulation, we did not produce or we don't have a manufacturing supply chain permanent magnet, right? So, so given that in mind, that there could be switched reluctance motor or synchronous reluctance motor or induction motor, but most often we resort to induction machines because induction machines have been around us over a century, right? We know them, we have good manufacturing facilities, they are easy to use, they last really long, they are reliable. So that's why we go for induction machine. Another reason is, but induction machine is heavier, less efficient, but less costly, right? And durable, reliable. So if
And
we can,
probably starting torque is also low. No?
yes, and also starting torque is low, but they are heavier, they are less efficient, right? So then one company came to us, they are manufacturer of aluminum, and their primary business is lightweighting. They said, hey, we can use our material to lightweight your induction machine and do research to improve the performance and efficiency, right? So then our recent project with that company has been on induction machine development. So at the end of the day, what I choose, I mean, I can choose either permanent magnet or induction because I feel either of those would continue to be used in electric cars. But if you want a smaller, lighter, more efficient machine, permanent magnet machine. If you want less costly, durable, reliable machine, induction machine. But they're heavier and less efficient, right? So through research, if we can overcome the disadvantages of induction machine technology and bring it close to the performance level of permanent magnet machines, then that's a big win. That's a breakthrough, right? So, and also I go where industry partners take me, right? Because they are the ones, they will bring funding, then I take the funding, go to the government, make the funding bigger. So it's mostly industry driven, right? So those are
Beautiful
the factors we take into consideration.
answer. Thank you, sir. Beautiful answer. Very, very nice answer. Thank you. But however, sir, induction machine can be made.
Achuta, I have in continuation another question.
Please,
Just
Gautam.
so,
Gautam, please.
okay, so I mean, this is really excellent, knowledge for all of us that effort for you know tending towards permanent magnet machines, even though induction motors are used and improving their performance, starting torque, etc. Um, I mean, maybe linked with this, you mentioned about the cooling system, and you also mentioned about CFD. So I would like to know whether are you developing CFD tools through your students or multidisciplinary students that engaged in this, or are you using softwares like Fluent, COMSOL, or Star CD and customizing them through your students?
So we have all sorts of softwares that we subscribe to. And when it comes to multidisciplinary part of it, materials, software, thermal, then usually I co-supervise students with professors from all those areas where they are the expert. So CFD analysis is done by another professor and I collaborate with him. But that is his main expertise, not
No,
mine.
Professor Kaur, that is appreciated. My question is little more inside. I am
Yes.
saying that
We have access to all
when you applying or when you are developing cooling system for a complex geometry.
Yes.
Now, usually in academic parlance, for example, if the problem is given to me, I would like to generate grid, I would like to develop my own code and all such things. But this is a approach which is little dated from the perspective of industry. It is good for academia, but industry needs quick solution. So maybe for the specific purpose, you may like to use a software, maybe ANSYS Fluent or Star City or any such. But definitely, when you bring a software, it has to be you have to develop, customize and develop user-driven subroutines, which can also be done by the students.
Yes.
And
Yes.
very effectively it can be made use of. I just wanted to know under such competitive situation whether you are going for writing the code on that approach, or you are customizing a software and writing user-defined subroutines for effective utilization in a very efficient and quick manner.
Yes, I think you already answered my questions that we have all the softwares, but whenever needed, we develop our own code to solve problems. We have access to all softwares. So if it needs customization, developing subroutines, or developing our own software, sometimes, say algorithm, you will find ready-made in MATLAB Simulink. But I tell students, develop your own, right? Write the code in your way to solve the problem. So we do all, I mean, it could be existing one, just using it, building model, running simulation, or customizing it, or developing something, adding to the software, or developing an independent, I mean, software-based program to solve a certain problem. So we are doing that as well. And if it is multidisciplinary, I also bring the other professor and sit down with them to develop that plan, that how we should proceed.
Thank you.
Thank you, Professor Kaur. I can add only one statement to you. In my life, I have found Excel as a wonderful tool. You can cut it any way you like. You make your own things using the base Excel, which is sort of you buy it with the computer. You don't pay much proprietary costs, but you can do almost any program, any structural, electrical, mechanical, any. You have got a problem, you can solve it with Excel, with your own template. Thank you. That's my point.
Achudha, probably field equations cannot be solved that way. See, these are parametric form of solution. When you require to solve a field, total field, Navier-Stokes equations cannot be solved or developed on Excel platform. Anyway, I'm not going to that, controversy or arguments.
Thank you both. Thank you, Dr.
I have a query near the Professor Kaur. Sudhir Ghosh speaking.
Oh, yes, please.
Yes, Professor Kaur. Does your team include people in working in fuel cell vehicle also?
Well, not my team, but we are developing a plan where we have professors that are working on fuel cell. I mean, Dr. Biswas is
Separate
aware
group.
of that. Yes, not in my lab. We do zero fuel cell research, but I mean, I work with
Because both Ford and Toyota, as you mentioned, Ford, Toyota, both are also working on fuel cell vehicle and fuel cell hybrid also.
Yeah.
Yes. So we think that's also an important area that needs to be looked into. So I brought together
So the focus of your group is
professors.
primarily pure electric. I think.
Yeah, my personal focus is electric powertrain. But there are other areas that I'm developing a pan-Canadian program with 11 universities with about 100 professors. So there is a module fuel cell development of low cost, high performing, durable fuel cell. So there is a component there. So we have 5-6 professors there working on that.
Okay. And on the battery front, are you also or any of the team in Windsor working on any future candidate beyond lithium ion? Or
Yes,
the total focus is
yeah, but there are, I mean, I am no expert to begin with, but again, I am developing that program I was referring to, that we have a huge group of people looking at various
Zinc care,
types of
let's say.
chemistries and materials. Then there is another group on battery cell development, and then another group on battery development, including cooling, including housing, battery pack tray, cover, lightweighting. So we are looking at all sorts of chemistries, including solid state. So from battery chemistry material that are traditional, that are sustainable, to cell processing characterization, cell development characterization, pack development characterization, housing, cooling, lightweighting. So we are looking into all of it.
Professor Kaur, can I make this comment that together with lithium-ion battery, the sodium-air battery is also a competitor.
Yes.
I mean,
Yeah, sodium, yeah, zinc air is also now coming.
Sodium-air is coming up very fast.
I have a project still ongoing, but it's kind of done. So one component was sodium-air battery in that project. Not mine,
and one
by another professor.
and one elementary query. I mean, technology-wise, be it four-wheeler or be it your two-wheeler, is the basic technology for electric vehicle, is it going to remain same more or less, apart from sizing?
Yes, it depends, I guess, where we are and what our requirements are, right? For two-wheeler, I mean, it's simple. I mean, at the end of the day, electric cars are simpler, right?
Yeah.
You have battery pack, you have a controller, you have an electric motor, and there you go. It's as simple as that, right? It's like I got an electric car for my home use. I got last June 1st, and today is July 19. Zero maintenance so far, right? And I have no maintenance planned for the next 1 year, right? So electric cars are simple, fewer number of moving parts. Only trouble is charging time could be long, costly. We don't know what is going
No,
to happen.
I mean to say, I mean to say the research indications that you gave. For example, the material front, you said using aluminium, you are able to reduce weight. I think to the extent of 60 or 67%. You mentioned somewhere. So I mean, is the same results could we directly apply for two-wheelers also?
Oh, yes, I think that was at the motor level.
On motor front, yeah.
Motor level, I mean, certain materials can improve performance by that, if I remember correctly. But two-wheeler, three-wheeler, four-wheelers, I think it depends on where we are. For example, in Canadian context or in North American context, I don't think you will see a lot of three-wheelers. May not be successful. Two-wheelers, we consider that as bicycle mostly here, and you will see a lot of electric bicycles. So that could be there. Just those who ride bicycles, an electric one or pedal assisted electric. There will be some market, but it's mostly traditional vehicles with four wheels that in North American context. But in other parts of the world, like I was in China. Right
in
before
Asian market, there is strong
there's a
strong
huge demand,
presence
yes.
of two-wheelers and the industry
Yes,
purpose.
yes, there you will see a lot of two-wheelers there, right? So it depends on where we are, right? The market and the development is market driven, right? So in North American context, three-wheeler, two-wheelers will remain a bicycle, just electric.
May I ask a simple question, please? May I ask a question? Hello.
This Dr. Palit, yeah.
No, I'm not doctor. It is a D Palit. I'm from B College. My simple question is something like this, that in electrical vehicle, the emphasis is on direct drive. You are putting either permanent bracket motors or the induction motors directly to the axle. But the basic principle is to get high torque at low speed and very low torque at high speed.
Yes.
So, that gives you certain range of speed and also torque. Now, in one of your slides, I found there is an application of a gearbox also. Now, by applying a high-low gearbox, that means a reduction gearbox and step-up gearbox, one can increase the range of the speed, make high torque, low speed even enhanced, and also higher speed can be enhanced. So is it not applied at all? Is it an exception? Or, your comment on it. That means
Yes.
whether it is high-low, a simple gearbox, is used along with the gear drive or not, direct drive or not? That is my
So
question.
in the case of larger vehicles like electric bus or truck, direct drive motor would make a lot of sense because space is not a constraint. For other types of vehicles, passenger vehicles or passenger minivans, vehicles like that, that you will mostly see an electric motor with a gearbox, gear reduction, because we want the motor to be uh, a high-speed motor, right?
Yeah.
High-speed motor means lower torque, but that reduction gear would lower the speed, improve the torque, right? So sometimes they're fixed gearbox, right? Sometimes 2-to-1, right?
Yeah.
Sometimes it could be any. So in an ideal world, that no gearbox is good as long as the motor is smaller, right? Since the motor
That is
cannot
understood. Okay.
but motor, if you don't use that gearbox, motor size gets bigger. So it's an optimization between having a gearbox attached to the motor or not, depending on the vehicle design, right? Another matter, you mentioned that higher torque at low speed. I mean, that these days we can achieve through control algorithm, that you can control we can split the current going into the motor into different components and control those components to have higher torque at low speed, lower torque at high speed. So we can achieve that through control, but that's a significant priority to have higher torque at low speed, because when you're accelerating, you need a lot of torque. So that can be achieved through design, number one, through control as well. Control plays a lot of role these days in terms of making the motor higher performing, higher efficient, right? We can control the motor in a high efficiency way, right? So through design and through control, we can achieve those.
So, putting gearbox is a rarity and mostly for
there is gearbox.
Heavy vehicles.
Yes.
Mostly for heavy vehicles?
Yes, most vehicles have a gearbox.
Okay, in a way that is understood, because when we drive our normal personal vehicles, compared to that, suppose it has got a normal conventional vehicle has got, say, a 4-speed gearbox or 5-speed gearbox. Whereas in those heavy vehicles, they go for 7, 8, 9 speed gearboxes.
Yes,
And
yes.
perhaps that is the reason they are putting a simple gearbox, maybe just high and low, or maybe a simple gearbox will help. I appreciate your
we have
insight.
multiple motors that we got from vehicles currently on the market, new vehicles. So all of them came with the gearbox, right? One with 9-to-1 reduction,
Yeah.
one with 10-to-1 reduction,
Correct.
right? You will also see vehicles with 2-to-1, right?
Yeah.
But again, higher that reduction, lower is the motor size, right?
Correct.
Professor Scott, that leads to another comment from my side. Is there any consideration of using CVT, continuous variable transmission, in electric vehicles so that there's no such different gear ratios as we do in our all modern cars? We don't have. I never know how to drive a stick box,
Yes,
but I drive my car without any problem because I have a CVT. Okay.
you might find
It's
CVT in some electric cars, but the idea is to make things simpler, right? That's why that you don't need a CVT. It could be complicated and expensive. As long as there's a reduction gear attached to the motor, it does the job. Then there is a control algorithm that can control the speed and torque of the motor, right? That's a control does most of the work, but the motors, because of the motor size, still need a gearbox, right? So that's why gearbox is there, but control will do the rest, right? So that's why we don't go for complicated transmission system.
Sunday, I got another quick comment, if you don't mind. I'm the rest of you. Are you considering anything about your recycling your batteries? Is there any research going on recycling batteries?
Oh, that's a big area. Again, I will go back to the big
that's
program.
that's a
with
gray
developers.
gray area as of yeah.
Well, this gray area has to be
Hmm.
not grazed sometime soon, right? Because that is going to be the bigger issue in the coming days. Even I will start with the smaller one, electric motor. You have a lot of materials you are using there, copper, right? That are we able to, after their lifetime, are we able to extract all those materials and recycle and use, right?
Yes.
When it comes to batteries, in many cases these days, we take the whole battery and just crash it and throw away, right? And that's a serious environmental concern. So the idea is, can we make batteries in a way easy to disassemble, right, after their lifetime, so that you can extract lithium, you can extract graphite, nickel, right? All other materials, the copper we are using in batteries, can we take them out easily in an automated way so that we can recycle them, right? So that's a huge area of research right now.
Okay, good. Thank you. Thank you very much.
Thank you.
Dr. Carr. Thank you, everyone. And I'm just trying to close this because I think we are almost.
Near the, if there is no more queries, then just at the end give me a couple of minutes just for Thanksgiving.
Absolutely.
I think there is no more comments.
Okay. Yeah. Please go ahead.
Then
Yes. Yes.
Thank you.
Please.
On behalf of the department and on behalf of the Centenary Celebration Committee, let me thank Professor Narayan C for this wonderful presentation here today. Most of us are from mechanical side, but still we could observe a lot of things, learned a lot from you. We hope to get you on some other forum here in at IIST. We look forward to more interactions. And recently, we saw a call for your, doctoral fellows or postdoctoral fellows. I think through such calls, there will be increased interaction between your group and our groups, both electrical as well as non-electrical side, on material fronts also, because the thermal issues are also involved in your research facility. So we look forward to more interactions, similar interactions. Let me also take this opportunity to thank Niyarda for giving your time from your busy schedule and for nicely leading this session for Dr. Kaur. So thank you both of you
Thank you.
from the department.
Our pleasure. Thank you.
At the end, I have a present responsibility on behalf of the Centenary Celebration Committee. We have a small memento and a digital certificate. If we can show the digital certificate, volunteers, yeah.
There we
So
go.
a copy of this we will be sending to the speaker through email, and we also have a hard copy and a memento which we will plan to will try to hand over through. So I mean, if Dr. Kaur happens to be at our place sometime nearer, that will be fine. Or else maybe when near they will be coming here, we will send it through near the.
That's beautiful.
Yeah.
Thank you. Thank you.
Thank
Thank
you.
you very much. Yeah.
I would also thank you. I mean, the contribution of IIEST to what we do here has been significant, right? We should not forget that.
Yeah, and 100 years at the beginning you were mentioning 100 years is for our department. For the university, it's
Yeah.
quite a lot.
To thank Niharda for what he has done to our program and to the relationship that we have built, IIEST
Yeah.
Windsor relationship. So
Yeah.
I will not undermine that because he is the main driving force, made all
Yeah,
these
and
things happen, right? So
for
I thank you
for
all for
today's
that.
lecture also.
And thank
For
you
today's lecture
for
also.
inviting me to this event.